Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to try something with me. It's a mental exercise to get us started.
Okay.
I want you to close your eyes right now, just for a second. Imagine you are standing in the middle of a vast open field.
Right.
You are miles away from the nearest city. No streetlights, no car headlights, just total absolute darkness.
Right.
And you look up.
The classic night sky. The one our ancestors saw.
Exactly.
Yeah.
For 99% of human history, that view was static. It was peaceful. It was empty.
Yeah, predictable.
You had the stars, the planets, the Milky Way, if you were lucky enough to be away from light pollution. It was a painting that didn't change. It was the definition of stillness. But now
It's different.
open your eyes, because that painting is gone.
It has been replaced by a highway.
That's a great way to put it. If you go out tonight and you have the right equipment, or honestly, even if you just have decent eyesight and look closely during twilight, that sky is buzzing.
It really is.
It is literally alive with movement. It's not just shooting stars anymore. It's hardware.
Yep.
It is human-made machinery streaking across the constellations.
It is infrastructure. That is the fundamental shift.
Yeah.
We used to look up and see nature, something eternal. Now we look up and see traffic.
And today is Monday, February 16th, 2026. And as we sit here right now, the sheer volume of metal circling over our heads is, it's staggering.
It is. It's hard to comprehend just how busy it has gotten in such a short amount of time.
So let's put a number on it.
To put a specific number on it, as of this morning, there are roughly 11,800 active satellites in orbit.
11,800, just, pause on that for a second. Nearly 12,000 distinct machines flying at 17,000 miles per hour, weaving around each other.
And that number, that 11,800, that's just the active ones. That doesn't even count the dead ones, the old rocket stages, the debris.
Oh, wow. Okay, so the actual number of objects is much higher.
Much, much higher.
That's already hard for me to wrap my head around. I remember when it was just a few hundred. But when I looked at the projections in the source material for today's analysis, that is when I actually got worried.
You are looking at the 2030 numbers.
I am. And they are, they're exponentially wilder.
They are. The current industry predictions suggest that by the end of this decade, so effectively, in just 4 years, that number isn't going to double. It isn't going to triple.
No.
It could skyrocket to over 100,000 satellites.
100,000. That isn't a highway anymore.
No.
That is a swarm. That is a cloud of metal encasing the planet. And this brings us to the absolute heart of what we are unpacking today, because there's a tension here, a conflict that I think most people, even those who follow space news, don't fully realize is happening.
It is the central tension of the modern space age. It is what researchers are now calling the space sustainability paradox.
The paradox. And this is the hook for today's exploration. Because on one hand, we are launching all of these satellites for noble reasons, right?
For the most part, yes.
We aren't just doing it for TikTok or high-frequency trading. We are trying to save Earth. We are monitoring climate change. We are watching crops to ensure food security. We are tracking disasters.
Precisely. We are building a nervous system for the planet. We are trying to give Earth a way to sense itself, to monitor its own vital signs.
But here is the kicker, the irony.
Yeah.
In doing so, in trying to save the environment down here, we might be destroying the environment immediately surrounding Earth.
That is the core of the paradox. It is a concept that has been heavily highlighted by researcher John McIntosh and his team at the University of Manchester. The argument is that the very tools we are using to solve environmental and social challenges on Earth could ultimately undermine the long-term sustainability of space itself.
It is a cruel irony, isn't it? We are so focused on cleaning up the ground that we are trashing the ceiling.
That is a very apt way to put it. And the danger is that if we aren't careful, that ceiling becomes unusable.
And if that happens.
And if the ceiling becomes unusable, we lose the ability to monitor the ground. It is a feedback loop of failure. If we break space, we lose the tools we need to fix Earth.
So the mission for this analysis is to look at a new breakthrough that might actually help us solve this paradox. We are looking at research coming out of the University of Manchester that proposes a way to keep an eye on our planet without turning low Earth orbit into a demolition derby.
It's a fascinating piece of work because it challenges how we have traditionally built satellites. It asks us to rethink the trade-offs between, what we want to see on the ground and the risks we take in the sky.
It seems to ask a pretty fundamental question.
It does. It forces us to ask, is the way we have been designing these missions actually the dangerous part?
And just a note for everyone listening, we are going to get into the weeds of this. We aren't just going to skim the surface. We are going to look at the physics, the decision-making models, and the surprising findings about where the most dangerous places in orbit actually are.
And spoiler alert.
Because spoiler alert, it is not where you think it is.
It certainly surprised me. The data is very counterintuitive. It challenges a lot of the assumptions even industry veterans have held for years.
So let's get into it. Let's start with the basics. The crowded sky. Why, and I mean, really, why are we putting 100,000 things up there? Is this just so I can have faster internet on my phone? Is it just about Starlink and Amazon Kuiper battling for dominance?
Well, internet connectivity is a big driver, certainly. The mega constellations for broadband are the ones that get the headlines because they launch in batches of 60 at a time. It's flashy.
Right, you see the rocket go up, you see the videos of them deploying.
But for this specific discussion and for the research we are analyzing today, the focus is really on Earth observation satellites.
Earth observation. So cameras in the sky, spying.
Well, monitoring is the polite term. But essentially, yes. However, it is much more than just taking pretty pictures or military spying. These satellites have become the critical tools for meeting the United Nations 17 Sustainable Development Goals, or SDGs.
The SDGs, okay. Those are the big global checklists for a better world, right? Zero hunger, climate action, life on land.
That's them.
I see the colorful icons everywhere, but I rarely connect them to space hardware.
You should, because you cannot fix what you cannot measure. That is the fundamental rule of engineering and policy.
Right.
If you want to solve zero hunger, you need to know where the food is growing, where it is failing, and why. That is where these satellites come in. They provide the raw, unvarnished data we need to verify if we are actually meeting those goals.
Can we get specific here? I want to visualize this. When you say monitoring, what are they actually looking at? Give me a concrete example. Let's take one of the goals.
Okay, let's take land use and urban development.
Right.
This is SDG 11. Sustainable cities and communities.
Okay.
Right now, cities in the global south are expanding at a rate that is almost impossible to track from the ground. You have informal settlements, slums popping up overnight.
And governments might not even know they're there. They don't have the paperwork.
Exactly. They don't have the census data. They don't have the resources to send surveyors out every week. But a satellite passes over every day.
Every single day.
It sees the new roofs. It sees the roads being cut into the forest. It sees where the infrastructure is failing. It can measure the heat island effect of a specific neighborhood.
Yeah.
We use that data for real-time urban planning on a planetary scale.
So it isn't just a map. It is a living document of human expansion. It helps them figure out where to put water pipes or schools or clinics.
Correct. It turns urban planning from a reactive process into a proactive one. Then look at environmental degradation. This is the big one.
Climate action, life on land, life below water, all of that.
All of it. We are tracking deforestation in the Amazon, counting the trees as they fall. We are measuring the volume of melting ice sheets in the Arctic to the cubic meter.
How is that even possible?
Using radar altimetry. They bounce signals off the ice and measure the return time down to the nanosecond. That tells you the height of the ice sheet, and you can see it shrinking over time.
That's incredible.
We are monitoring the health of coral reefs by looking at the color of the water. We can even track illegal fishing boats by spotting ships that have turned off their transponders.
So it's accountability.
It's accountability and it's measurement. You can't have a climate treaty if you can't verify if a country is actually reducing its emissions or protecting its forests. This is the verification system.
And disaster response is a huge one, too. I remember reading about this during the last big earthquake season.
It is critical. It's one of the most immediate life-saving applications. When an earthquake hits or a hurricane makes landfall, the roads are gone. The power lines are down.
Chaos on the ground.
You cannot send a guy in a Jeep to check the damage. The first thing emergency responders ask for is the satellite pass.
They need the before and after photo to see where help is needed.
They need a damage map. They need to know which bridges are out, which neighborhoods are underwater. That coordination of aid, getting the water and medicine to the right place in the first 24 hours, saves thousands of lives.
Wow.
And that coordination happens because of eyes in the sky.
It connects back to food security, too, doesn't it? The zero hunger goal.
It does. This is arguably the most sophisticated usage. We aren't just taking photos of cornfields to count the acres.
Did more than that.
Oh, much more. We were using hyperspectral imaging. We look at wavelengths of light that the human eye cannot see.
What does that tell you?
It tells you everything. We can look at the moisture levels inside the soil from orbit. We can see the chlorophyll content in the leaves, which tells you how healthy the plant is.
So you can spot a blight or a drought before it's visible to a farmer on the ground.
Exactly. We can predict a yield shortage in wheat across the entire Ukrainian breadbasket months before the harvest actually happens.
That is incredible. So in a world with a growing population and a climate that is getting more erratic, that data is essentially preventing famine.
It is.
It tells governments, hey, you are going to run out of food in 6 months, buy grain now.
Exactly. It smooths out the shocks to the global food system. And speaking of shocks, the sources also mention supply chains.
Ah, yes.
Remember the Ever Given? The ship that blocked the Suez Canal.
Hard to forget the meme of the year.
Satellites were tracking that back up in real time. If you can see that a port in Shanghai is congested or a key route is blocked, you can anticipate economic shocks. You can reroute cargo. It's the backbone of global logistics. Okay, so when we talk about these 100,000 satellites, we have to be clear. We aren't just throwing them up there for fun.
No.
We aren't just doing it because we can. We rely on them. They are the nervous system of our modern civilization.
They really are. If you turned them off tomorrow, we would be flying blind on climate, on agriculture, on disaster relief.
We would be back to the 1950s in terms of our situational awareness.
We would be reacting to disasters after they happen instead of seeing them coming.
Okay, so we have established the stakes. The why is solid. We need the data.
Yeah.
But, and here's the massive but we teased earlier, there is a cost of doing business.
There is always a cost. Physics demands a trade-off.
The rapid growth of these missions is making Earth's orbits, specifically low Earth orbit or LEO, crowded and hazardous.
Hazardous is a polite way of putting it. It is becoming a minefield. Break that down for me. When we say hazardous, are we talking about traffic jams? Like, are satellites waiting at a red light?
That's chuckles. I wish it were that simple. No, imagine a highway. But on this highway, everyone is driving at 17,000 miles per hour.
Okay.
That is the speed required to stay in orbit. If you slow down, you fall out of the sky. So you have to go fast.
17,000 miles per hour. That is, what, 10 times faster than a bullet?
Roughly, yes. And on this highway, there are no lanes, there are no stop signs, there is no air traffic control telling you to turn left or right in real time.
And no brakes.
And no brakes. And, crucially, occasionally a car just falls apart and leaves its bumper in the middle of the road.
And because there is no air drag to slow it down, that bumper just keeps flying at 17,000 miles per hour.
Precisely. It stays there for years, maybe decades, maybe centuries, depending on the altitude. That is the threat of space debris.
So even something tiny is a problem.
In space, a collision is catastrophic. It isn't a fender bender where you pull over and exchange insurance info.
It's just total annihilation.
When two satellites collide, or when a satellite hits a piece of debris the size of a marble, it doesn't just dent. The kinetic energy involved is insane.
Right, the physics.
Remember your high school physics. Kinetic energy equals 1/2 mass times velocity squared. When the velocity is 17,000 miles per hour, that v squared term is enormous. So even a tiny mass hits with the force of a hand grenade.
A hand grenade.
It obliterates the object and creates a cloud of thousands of new fragments.
Which then go on to hit other things. This is the Kessler syndrome, right? The runaway chain reaction.
That is the worst case scenario, the domino effect. One collision creates debris, which causes two collisions, which creates more debris until the entire orbit is ground into dust. It creates a shell of shrapnel around the Earth.
And if that happens?
If that happens, we lose space. We cannot launch through that cloud. We lose GPS, we lose the weather satellites, we lose the climate monitoring. We are trapped on Earth.
That is terrifying. So by trying to monitor the Earth to save it, we are clogging up the viewpoint we need to do the monitoring.
That is the space sustainability paradox in a nutshell. We are risking the very environment we need to utilize.
Okay, so we have established the stakes. We need the data, but getting the data is risky. Now let's talk about why this is happening. Is it just that we are launching too many? Or is there a flaw in how we are designing these things?
It is a bit of both, but the research from the University of Manchester highlights a fundamental flaw in the traditional design process.
A flaw in the thinking.
Exactly. It suggests we've been doing the engineering backwards.
How does it usually work? If I am an engineer at a big aerospace company, Lockheed, Boeing, Airbus, and I am told to build a new climate satellite, what is my process?
Traditionally, there is a disconnect, a siloed approach. You start with mission requirements.
Okay.
Your client comes to you, maybe it's a government, maybe it is a company, and says, I need to see a car on the ground in Tokyo. Or I need to measure the ice in Antarctica, and I need the data back to headquarters in under 10 minutes.
So you focus on the payload, the camera, the antenna, the power.
Exactly. You design the payload to meet those needs. Can we get the data? Is the resolution high enough? Is the bandwidth fast enough? That is the priority. That is what you get paid for. That is the success criteria for the mission.
And safety. Where does safety fit in?
Collision risk assessment often happens separately. Or, critically, it happens too late in the development process.
So it's an afterthought.
It is treated as a regulatory box to check. You build the satellite to do the job, you decide where it needs to fly to get the pictures, and then you check, oh, is this orbit safe?
It is like designing a sports car that can go 200 miles per hour, building the engine, the chassis, the wheels, and then realizing at the very end, oh wait, this thing has no brakes and we are driving on ice.
That is a surprisingly accurate analogy. You have locked in the design parameters, the size, the mass, the orbit, before you have really calculated the long-term risk to the environment.
And at that point, it's too late to change it.
Well, it is often too expensive to redesign the whole bird. So you might tweak the orbit slightly, but largely you launch anyway and hope for the best.
And that brings us to the innovation we are analyzing today. This new research published in Advances in Space Research. Who are the brains behind this?
The team is from the University of Manchester. You have the lead author, John McIntosh, who is a PhD researcher doing some really cutting-edge work. Then there is Dr. Sierra McGrath, a lecturer in aerospace systems, and Professor Catherine Smith, a professor of space technology.
A solid lineup. Academics, but with a focus on systems engineering. Practical application.
Very much so.
Yeah.
And what exactly have they built? It is not a new type of shield. It's not a laser to zap debris.
Right. It's not a physical thing.
No, it is something much more boring and much more important. They have developed a new modeling framework.
Okay, hold on. Modeling framework sounds like jargon. What does that actually mean in plain English?
It means they built a simulator, a decision-making tool. The key breakthrough here is that it links mission objectives directly with collision risk as a key first step in mission design.
So before they even draw the blueprint, before they cut a single piece of metal, they are calculating the risk.
Yes. Instead of treating safety as an afterthought,
It's a core design parameter.
it treats safety and image quality as interconnected variables. You cannot change one without affecting the other. It forces the engineer to see the consequences of their design choices immediately.
This sounds like it should have been obvious, but I guess when you are in a gold rush, you don't think about the dust you are kicking up.
It is a shift in mindset. It moves from performance first to sustainable performance. And that is a huge leap for the industry.
I want to get under the hood of this model. They call it a framework, but I want to visualize it. How does it actually work? What connects a picture of a cornfield in Iowa to a collision in space? Because those feel like two very different problems.
To understand that, we have to look at what I like to call the iron triangle of orbit. The model breaks down several inputs that are all mathematically linked. First, you have image resolution.
This is the quality of the camera, the sharpness of the picture.
Right. How clear does the picture need to be? Do I need to see the cornfield as a green blur, or do I need to see the individual stalks of corn?
High resolution versus low resolution.
Exactly. In the study, they use an example of 0.5 meters. That is the ground sampling distance. It means each pixel in the digital image represents half a meter on the ground.
That is sharp. That is sharp enough to see cars, small structures, agricultural lines.
You could count the tents in a refugee camp with that.
You could probably tell what kind of car it is, but not the license plate.
That's a good way to think about it.
Yeah.
It is the standard for high-quality commercial observation. So that is input one.
Okay. What else goes into the simulator?
Coverage. How much of the Earth do we need to see, and how often? Do you need a global map every single day, every hour, or just once a month?
So the revisit rate.
The revisit rate, exactly. This determines how many satellites you need in your constellation.
Got it. Frequency and scope.
Then you have the satellite physicality, the size and the mass of the actual machine. How big is it? How heavy is it? And finally, the debris density of the neighborhood you want to fly in. So how much junk is already in that specific orbital shell?
Okay, so we have all these variables: resolution, coverage, size, debris. How do they interact? Because this is where the physics of optics comes in, right? And I feel like this is where the trade-offs get really tricky.
This is the crux of the problem. This is where the Manchester team really showed their work. Let's say you are the engineer. You have a requirement. You need that 0.5-meter resolution image. You cannot compromise on that.
Okay. I need the sharp photo. That is my job. Non-negotiable.
You have two main options to get it. Option A, you fly low.
The low option, you get closer to the subject. Makes sense.
Right. If you are closer to the ground, say at 300 or 400 kilometers altitude, you can use a smaller camera to get a sharp image. Think about it like holding your phone camera close to a piece of paper. You can see the details easily.
Okay. So smaller camera means?
A smaller satellite, a smaller lens, a smaller body, lighter launch weight, cheaper.
Okay. Benefit. Clear picture, smaller satellite, cheaper launch. What is the drawback? There's always a drawback.
The drawback is your field of view. Because you are so close, you are only seeing a tiny patch of the Earth at any one moment.
It is like looking through a straw.
Exactly. You are looking through a straw at a giant beach ball. You can see the details of one little grain of sand, but you cannot see the whole beach ball. So if you want to cover the whole Earth,
You need a lot of straws.
you need a massive constellation of satellites to stitch it all together, hundreds, maybe thousands of them.
Okay, so low orbit means small satellites, but lots of them. A swarm. What is option B?
Option B, you fly high, you go to a higher altitude, say 800 or 900 kilometers.
So you are further away.
The benefit is you have a much wider field of view. You are backing up from the painting, you'd see more land at once.
Right. Your straw just got wider.
It did. That means you need fewer satellites to cover the globe.
That sounds better. Fewer satellites means less traffic, right? That sounds like the responsible choice.
You would think so. But here is the kicker. Here's the trade-off. To get that same 0.5-meter resolution, that same sharpness from twice as far away, you cannot use a small camera anymore.
Physics bites back.
It does. It is the diffraction limit of light. To resolve that detail from 900 kilometers, you need a massive telescope. You need a large aperture to gather enough light and achieve that resolution.
We are talking Hubble-sized.
Maybe not Hubble, but big. You need bigger mirrors, longer focal lengths, and bigger optics means a bigger satellite body to hold it. Bigger solar panels to power it because it takes more energy to transmit the data that far.
So high orbit means fewer satellites, but they are giants. They are buses instead of motorcycle.
Correct. Significantly bigger, heavier. And this brings us to the critical variable in the Manchester model, cross-section.
Cross-section. That is basically how big of a target you are, how much area you present to the incoming traffic.
Yes. A larger satellite has a larger cross-section. It takes up more physical space in the void. And in a minefield of debris, being big is a liability.
It is the difference between walking through a hailstorm, holding a dinner plate over your head, versus holding a barn door.
The barn door is going to get hit. And remember, we aren't just worried about the satellite getting hit. We're worried about the satellite becoming debris.
Ah, yes, the aftermath.
If a 500-kilogram satellite hits something, it creates a massive cloud of shrapnel. If a 5-kilogram CubeSat gets hit, it is bad, but it's a much smaller cloud.
This is starting to make sense. The model is balancing the number of satellites against the size of the satellites, against the altitude. It is a three-dimensional balancing act.
And this is where the findings get really surprising. Because I think most people, myself included, would assume that the most dangerous place to put a satellite is simply wherever the most debris is.
Right. Avoid the trash. If there is a pile of junk at 800 kilometers, don't fly at 800 kilometers. That seems like common sense. Like, don't drive into the pileup.
But the model reveals a counterintuitive truth. Collision risk does not simply peak where debris is most concentrated.
Okay, unpack that. How can that be true? If there are more bullets, shouldn't there be more bullet holes?
Let's look at the case study they ran. They modeled that satellite we talked about, the one designed for 0.5-meter resolution. They ran the numbers for different altitudes to see where the risk was highest.
And what did they find? Where's the danger zone?
The collision probability was highest between 850 and 950 kilometers above Earth.
850 to 950, okay. Is that where the most debris is?
No. That is the fascinating part. The peak density of debris, the thickest part of the trash cloud, is actually about 50 kilometers lower than that, around 800 kilometers.
Wait, so you were telling me that the satellites are more likely to get hit in a region with less debris? That sounds impossible. My brain is not computing this.
It sounds impossible until you factor in the size of the satellite.
Ah.
Remember the high option. To fly at 850 kilometers and still get that sharp picture, your satellite has to be enormous.
Ah. So even though the bullets are slightly fewer and further between, the target is so much bigger that the math tips against you.
Precisely.
Yeah.
You moved to a slightly quieter neighborhood, but you built a house 10 times the size. So you are actually more likely to get hit by a stray baseball than if you had stayed in the busy neighborhood but lived in a tiny shack.
That is a massive aha. moment. It changes everything. You cannot just look at a debris map and say safe or unsafe.
No, the debris map is only half the story.
You have to look at your own vehicle. Your own mission requirements dictate your vulnerability.
You have to look at the interaction. The sheer size of those high-altitude satellites makes them what the researchers call debris magnets. They sweep up everything in their path just by existing.
Wow. So let's talk about the alternative then. If the big, high-flying satellites are debris magnets, does that mean the swarm of small, low-flying ones is actually safer?
That is the constellation conundrum. And the model suggests counterintuitively.
Yes. Walk me through that, because earlier I said 100,000 satellites sounds terrifying. How can more satellites be the safer option? It just feels wrong.
It comes down to the physics of the impact and the probability. In lower orbits, say 400 kilometers, yes, you need more satellites to cover the Earth because of that looking through a straw effect.
Right. Many small straws.
But because they are close, they can be small. They have small optics, small bodies.
Tiny targets.
And because they are tiny targets, the individual collision risk for each satellite is much, much lower. And this is crucial. If they do collide, they create less debris because there is less mass involved.
So even though there are more of them, the odds of any single one of them causing a global disaster are smaller, and the consequences of a crash are less severe.
Yes. The study found that despite there being more of them, the smaller individual satellites are less hazardous in terms of collision probability compared to the massive high-altitude targets.
That is fascinating. It is a total flip of the script. We usually think less is more when it comes to sustainability, but here, more but smaller might be the responsible choice.
It allows designers to evaluate trade-offs in a nuanced way. It is not just about data quality anymore. It is about balancing data quality with protecting the orbital environment.
So an engineer can now go to their boss and say, look, I know you want to launch just 10 satellites for this mission because it's cheaper to operate, but the model shows if we launch 100 smaller ones at a lower altitude, the long-term risk to the space environment drops by 80%.
That is exactly the conversation this tool enables. It proves that you cannot just optimize for one variable. You have to optimize the whole system for sustainability.
And this brings us back to the voices behind the study. What are they saying about the implications of this? Because this sounds like it should be mandatory reading for everyone at NASA and SpaceX and, well, every space agency and company on Earth.
It really should be. Dr. C.R. McGrath, one of the co-authors, really emphasized the practicality of this. She said this method offers a practical way to ensure space remains safe and usable for generations.
That word practical is key. This isn't just theoretical physics. This isn't just an academic paper to sit on a shelf. This is a tool engineers can use tomorrow.
Exactly. It's a dashboard. You can slide the dial on resolution and see the risk needle go up or down. You can change the altitude and watch the constellation size and satellite mass numbers change in real time.
That's powerful.
It allows us to still get the data we need for those global challenges, climate, food, disasters, without sacrificing the future of space exploration. It gives us a path to have our cake and eat it too.
And Professor Catherine Smith pointed out that this isn't just for one type of satellite, right? It's adaptable.
Right. She noted that the method can be adapted for different Earth observation systems, whether you are using optical cameras like we've been discussing or something like synthetic aperture radar, SAR, which can see through clouds.
Which is critical for monitoring places that are always cloudy, like the tropics or the poles.
Exactly. The logic still holds. You can plug in your variables and see where your risks are. It's a universal toolkit for sustainable design.
So what is next for this model? Is it finished? Or is this just version 1.0?
Science is never finished. This is definitely version 1.0. The team plans to expand the model to include even more detailed impacts. For example, they want to look at how long debris fragments stay in orbit.
Because that changes based on altitude, right?
Drastically.
Yeah.
If you are low at 400 kilometers, there's still a tiny bit of atmosphere.
Yeah.
That atmospheric drag pulls the debris down quickly. It deorbits and burns up in a few years.
So it's self-cleaning to a degree.
It is. But if you are high up at that 900-kilometer danger zone, there is basically no drag. That debris can stay there for centuries, millennia even.
So a crash at 900 kilometers is a permanent scar. A crash at 400 kilometers is a temporary scratch.
That is a perfect way to put it. And they want to model the domino effect, how likely fragments from one collision are to hit other satellites.
The nightmare Kessler syndrome scenario.
Exactly, to model how a single bad day could cascade through an entire constellation. And they also want to look at the wider environmental effects of satellite reentry.
Re-entry. That is when they burn up in the atmosphere at the end of their life.
Yes, and that is a whole other can of worms.
We will get to that in a minute. I have questions about that. But sticking to the model for now, the ultimate goal here seems to be giving mission designers the full sustainability picture.
It is about moving from a Wild West mentality of space exploration, where you just launch whatever you want, wherever you want, to responsible stewardship.
Responsible stewardship. I like that. It feels like we are finally growing up as a spacefaring civilization. We are realizing that we cannot just trash the place and move on.
We have to manage the commons. Space is a shared resource. If one company pollutes an orbit, everyone suffers. This model gives us the math to prevent that.
I want to circle back to something we touched on earlier. The sheer scale of this. 100,000 satellites. Even with this model, even if we design them perfectly, that is a lot of traffic.
It is. And this model doesn't solve the crowding issue entirely. It just helps us mitigate the risk of catastrophic collisions.
It's a risk reduction tool, not a magic wand.
Exactly. We still have to manage the traffic management aspect. We need better tracking of every object, better communication between operators, maybe even internationally agreed upon slots for orbits, like we have for airport gates.
It is like having safer cars on the road, which is great, but you still have a traffic jam.
Exactly. But at least the cars aren't exploding as often.
That is a start. So let's synthesize what we have learned today, because this has been a journey from the night sky to the physics lab.
Let's break it down.
First, the context. We are heading toward a world with 100,000 active satellites. That is happening. The train has left the station.
And we identified the space sustainability paradox. We are launching these machines to solve problems on Earth, critical problems like climate change and hunger. But the act of launching them creates a new environmental disaster in space.
Then we looked at the Manchester research. They proved that the old way of designing satellites mission first, safety later, is broken. It's fundamentally flawed. You have to do them together.
And we unpacked the iron triangle. We learned that to get high-resolution images, you either have to fly low with lots of small satellites or fly high with a few giant ones. There is no magic cheat code.
And the counterintuitive finding, the real mind-bender. Flying high seems safer because there is slightly less debris, but because your satellite has to be the size of a bus to take a picture, you are actually a bigger target.
So, surprisingly, a constellation of many small satellites in a lower, busier orbit might actually be the safer, more responsible choice for the orbital environment.
It really challenges your assumptions. I think that is the mark of good science. It makes you look at a problem and realize the obvious answer was wrong.
And it gives engineers a tool to make better choices. That is the most important part. This isn't just philosophy. It is engineering. It's a practical solution.
Now, before we let you go, you mentioned something earlier that I want to end on. It's been nagging at me. You mentioned satellite reentry as the next frontier for this model.
Yes. This is the final provocative thought I want to leave with you and with everyone listening.
Lay it on us.
We spent this whole time talking about collisions in space. Metal hitting metal, debris fields. That is the physical danger. But what happens when these satellites die? All 100,000 of them eventually.
They deorbit. They fall back to Earth. We design them to burn up so they don't hit someone's house.
Right. We view burn up as the safe option. It burns up, it is gone. But physics tells us matter doesn't just disappear.
Conservation of mass.
Exactly.
Yeah.
Burn up implies it vanishes. It doesn't. It turns into vapor. It turns into dust. It turns into tiny metallic aerosols.
The metal vapor.
Aluminum, titanium, lithium from the batteries, composite materials, all of that 100,000 satellites worth of metal. Eventually, it all rains back down into our upper atmosphere.
So we are essentially salting the atmosphere with metal dust.
Exactly. We are changing the chemical composition of the stratosphere, and we don't fully know what that does yet.
That's a terrifying thought.
Does it affect the ozone layer? Some studies suggest aluminum oxides can act as catalysts that deplete ozone. Does it change the albedo of the Earth? Does it create more clouds or different kinds of clouds? Does it reflect sunlight or trap heat? Does it affect the climate?
So the sustainability paradox might go even deeper. We launch satellites to monitor climate change, and when they die, their dust might accelerate climate change.
That is the next great unknown. That is the environmental effect of satellite reentry. And that is why the Manchester team wants to add it to their model. Because true sustainability means looking at the entire life cycle, from the launch pad to the orbit to the burn-up.
That is heavy, but it is important. It means we have to keep asking questions. We cannot just pat ourselves on the back for solving the collision problem and ignore the pollution problem.
Precisely. There's always another layer to the onion.
Well, On that cheerful but necessary note, we're going to wrap up today's exploration. I want to thank you for listening.
It has been a pleasure to analyze this with you.
Next time you are outside at night, look up. Try to spot a satellite. It is actually pretty easy these days. And when you see that little dot moving across the stars, remember, there is a massive amount of math, physics, and now, hopefully, some very smart sustainability modeling keeping it from crashing into its neighbor.
Let's hope so.
The sky is busier than it looks, but with tools like this, maybe we can keep it organized. Thanks for joining us on this analysis. Stay curious.
And keep looking up.